There we go. All right, class, let's get started, y'all. So here's your exam from last time, completing the square, okay? What we're gonna do is we're going to focus on this part. We're gonna set this aside for a second, all right? If we look at this, really we wanna get this x squared kind of by itself, so we're gonna pull a 2 out here. So we have an x squared plus 3 halves x. And I'm going to make some space, and I'm just going to put a plus 4 over here. What we want is we want this to be something like x plus something squared. That's what we want, okay? So what we need to do is we need to add something in here to make this thing a complete square. Now remember, let's do this. X plus p squared is x squared plus 2xp plus p squared. So let's put another step in here first. So I'm going to rewrite this as x squared plus 2x times 3/4. Now, why did I do that? I mean, 2 over 4, it's still, this is 3 halves x, but why would I write it like that? All right, I wrote it like this because of this pattern here. We have x squared plus 2x times p, and then plus p squared. This is the p. I need to have that number squared, right? That's what I want. But I can't just put this here. I can't just add something if I'm going to maintain equality, right? So what did I just add in? I added twice that. So I also need to subtract twice that. Okay? Again, I've got x squared plus 2x. I needed a p plus p squared in there. Okay? So that's why you rewrite it like that. And again, I added something and I subtracted the same amount away. So all I did was add 0. And why did I do that? Well, that's because this is now just x plus 3/4 squared. I completed the square. And then this, I can just simplify all this stuff. This is, let's see, 2, let me put my minus here, minus 2, 3 squared is 9, 4 squared is 16. So let's do some more simplification. I got x plus 3/4 squared, and then let's just simplify this stuff. 2 times 9 is 18, right? 4 would be, the hell is it? 4, I need to get 16 over 16. What's 4 times 16? 4 times 16. 64. 64 fourths minus 18 fourths. Make some more room. Which is still this stuff. 64 minus 18 is 46. So plus 46 fourths. And we can simplify that fraction. Let's see, 46. Do it down here. 46 fourths. 46 is what? 2 times 23. So this is plus 23 halves. All right, assuming I didn't make any mistakes. Let's check our work here. So I wrote this as, I pulled the 2 out of here. So this is x squared plus 3 halves. So 2 times 3 halves is 3x. That's right. I kept my 4 over here. All right, so this guy, I rewrote this as this. So 2 over 4 leaves me a 2 on the bottom, a 3 on the top. So that's correct. And then I added this guy in because this is my p-value. I need to have a p squared there. So I can't just add it in. I also have to subtract it out. And so it's 2 times 3/4 squared. All right, so I got my 2. This thing is exactly x plus 3/4 squared. I still have my 4. This guy, 3 squared is 9 times 2 is 18, and 4 squared is 16. So that looks right. And 4 is, yeah, 64. Yeah, right here I screwed up. This is 16th. I knew that answer didn't look right. I multiplied this by 16 over 16. So that makes this wrong and this wrong. We don't even need that. What is 64 minus 18? I just had it. 46. 46 16ths. So 46 16ths. Let's simplify this fraction. 46 is 2 times 23. 16 is 2 times 8. So this guy. Just simplifying this gives me 23/8. So we completed the square. What does that mean, complete the square? Well, we have the x squared here, but we want it to look like x plus something squared. So that's completing the square. We'll do some more examples here in a minute. We'll do some simple examples and then build up to more complex ones. So this guy, I need to get this x by itself, so I'll factor out a -2. So this would be a minus 2x. And then I have plus 2. So that's step 1. I just get the x squared by itself, right? -2 times -2 is a +4. Okay. So I'm just gonna do it down here. Let's get us a whole new page here. I'm gonna move this up here and move this down here. There's plenty of room. There we go. So now I'm gonna take this guy here and I'm gonna rewrite it as x squared plus 2x times a -1. Why did I do that? Because x squared plus 2x, this number I need to have right here squared. I need to have this number squared. But I can't just add that unless I'm willing to also subtract it, right? So what did I just add? -1 squared is 1 times a -2. So what I did there is I just put in a -2, so I need to add 2 back. Does that make sense? That's 1 times -2. I just put a -2 in there. So I need to add that 2 back to balance it out, so I maintain equality. So what is this? This is -2. This guy is x minus 1 squared. 2 plus 2 is 4. All right, completing the square. Yes. Because this right here is a -2x. So I needed to write it as plus 2x times something. So the something was a -1, because -2x is positive 2x times a -1. All right. For the same reason up here, I rewrote this as 2x times 3/4. This is the number I had to have squared. All right. This one, it just happened to be just a -1 that I needed to put in there. Does this make sense? Completing the square. All it is looking at this. Okay. So let's do quiz daily. Quiz number 10. Complete the square. We'll do number 1. Let's do x squared plus 3x. For 2, we'll do 2x squared plus 4x. I'm going to give you a third one. 3x squared plus 2x plus 1. So I won't throw any negatives in there to mess with you, all right? Let's do 3 problems today. And we'll take 10 minutes to be enough time. So 5:52. We will work on these together. All right, so completing the square, this one should be easy, right? Number 1. So remember that I wrote x plus p squared is x squared plus 2xp plus p squared. So we need to make this look like this. We'll rewrite the 3x as what? A 2x times 3 halves, right? So, and I forgot my plus sign. Okay, so now looking at this, we have x squared plus 2x. This is going to be the letter p. So what we need to do is add 3f squared and also subtract it. So we're maintaining equality. This is just 0. Okay. So what we have is this thing right here is x plus 3 halves squared. And then we have minus this. Minus 3 squared is 9, 2 squared is 4. Easy enough? Right. That's the easy one. There's nothing else there to complicate it. Right. I'll color code it. This is this. Okay. So now this guy, I threw some 2's in there. Let's factor out a 2 first. This is x squared plus 2x. Right? So what is the p here? What is the p value? I'll write this as 2 times 1. Right? What I really need is a 1 squared here. But I can't just put that there unless I also subtract it. 1 squared is 1. I multiply it by 2. So I just added 2 in there. So I better subtract 2. Okay. So I factored out the 2. Right. This is just this. But I wrote it, since the 2x is already there, I needed a number p, so I just multiplied it by 1. So that means the number here I need is 1 squared. Of course, it's just 1. So what do I have? I have a 2. This thing is x squared plus 2x plus 1. That's just x plus 1 squared. And then I have a minus 2 left over. Right? Think about it. X plus 1 squared is x squared plus 2x plus 1. That's what this is. X squared plus 2x plus 1. Right? You can multiply it out and check your work. You can always do that. Now let's look at this one. There's a little. Move all this up 1 notch. Going up. Move you up 1 notch. And move you up a little bit. So this guy, let's get this 3 off of the back of the x here. So this is 3 times x squared plus 2/3 x plus 1. So first thing I did was factor out the 3. So now let's rewrite this as 2x times something. It would have to be times 2/6. 2 over 6 is 3, and we have the 2 on the top. So I wrote this like this. So that tells me what I need to add in here is a 2/6 squared. can't just add it unless I also subtract it. But remember, there's also this 3. So I need to subtract 3 of 2/6 squared. Okay. So this guy is now just x plus 2/6 squared. 2/6 is 1/3, isn't it? Let's go ahead and just reduce that fraction to 1/3. And now we just have to simplify this. So 2/6 is 1/3. So 1 squared is 1 times 3 is 3. 3 squared is 9. This is 3 times x plus 1/3 squared minus 3 over 9 is 1/3. Got it? Completing the square. All right, you'll have to do this on the final. Because copying down answers and not learning anything is not going to help you. Yes. So multiplying by 1, like right there. So let's focus on this one here, right? So this, to get the x squared by itself, I factored the 2 out, right? Here, I could put another step in here if you want. So this is 2 times x squared plus 2x, right? So now I'm focusing on this. I need to write it as x squared plus 2x times something, because it's that something that I need to add in squared. So the 2x is just by itself, right? So what is the number p? It's got to be 1, right? 1 times 2x is the same thing as 2x, right? So that's the number that I need to add in squared, just the number 1. Right? That makes sense? It's weird looking, right? We write a 1 in there. All right, so like this one. Okay, so this one, the first thing we did was we got the x squared by itself by factoring out the 3. So now we're focusing on this in here. So the next step is to write this as 2x times something, right? We write 2x, and what is the something? Well, we got the x, so this times this had better be 2/3, right? Well, 2 times 2 is 4 over 6. 4/6 is 2/3. That makes sense? So now that I have it in the form of 2x times a number, I know that the number I need to add in is this number and then square it. But now that I just added this in there, I have to make sure I subtract it out. Because I didn't just add in a 2 over 6 squared. I added in 3 times that. That's why I have to subtract 3 times that. Make sense now? A little better? Yeah, it's a lot of this is just pattern recognition or practice, you know. All right, so let's see, we are in section 2.4, I think, right? The last one we just did was 2.3. Let's knock out 2.4 here. Polynomial and rational functions. All right, polynomials, nomials. There we go. Here's some examples. 2x squared plus 3x plus 1. Here's another one, x to the 4th. Here's one, 3x to the 4th plus 2x minus 3. Right? These are all polynomials. Right? The way we would generically write it, because you can have any power you want to x. We would write this as x to, I'll put a sub n, now I'll call it c. C sub n plus c sub n minus 1 times x to the n minus 1 plus c sub n minus 2 times x to the n minus 2, all the way to c sub x to the 0. That's what polynomials look like. Now, why did I write it like this? Notice I have the highest power here, and then I go lower and lower and lower, right? I could have x to the fifth plus 2x to the fourth plus 3x to the third plus 2x or something like that, right? All this is saying is take x to the power. The c sub n, that's just the name of the number in front of the highest power of x. So for this guy, n is equal to 4. C sub n is 3. Now I could have said A, B, C, D, but you run out of letters, right? So these are the coefficients, the numbers in front of your x's, those are your coefficients. So all this is saying is, here's the coefficient that goes along with the highest power of x. This is the name of the coefficient that goes with the next highest power, right? So something like x to the fourth is really 1 x to the fourth plus 0 x cubed plus 0 x squared plus 0 x to the first plus 0 x to the 0 power, right? So in this case, n would be 4, c sub 4 would be 1, c sub 3 would be 0. All the other c's are 0 for this example, all right? So this is generically how we'd write. This is what every polynomial, the form of any polynomial looks like that. It's a constant times x to a power plus a constant times x to the next lowest power plus a constant times x to the next lowest power until you run out of x's, right? This is how we generically say things. And a rational function, remember, so let's say this is a polynomial function. Well, a rational number, right? Remember what a rational number is? 2/3, 1/5, 2, which is the same thing as 2 over 1. Any whole number over a whole number is a rational function. I mean, a rational number. So a rational function is if you have a polynomial over a polynomial. They call that a rational function. So here they're thinking of a polynomial as if it's like a whole number. Polynomials are like our favorite like functions. You know what I mean? So if we think about like a polynomial over a polynomial, we call that a rational function because it's a quotient, it's a ratio. So these are going to look a little different. So y'all are used to, y'all can graph x squareds and stuff now, right? Did we do that already? Did we graph quadratics in here? Kinda. It's just the x squared. We did the quadratic formula. We didn't finish that section, did we? No, we better check because that was supposed to take 2 days. I'm pretty sure we didn't quite finish it. Yeah, we might do that because you have to be able to graph these things. So we did completing the square. That way you could rewrite a quadratic as a completed square and treat it as transformations, right? All right, so let's backtrack a little bit here. I'll show you how to graphing quadratics. So let's back up. Okay. So if I give you something like f of x equals x squared plus 2x plus 1, and I say graph this. Well, you could use your completing the square trick to say, well, this is the same thing as x plus 1 squared. So it looks like x squared, but it's shifted to the left by 1, right? Okay, well, let's say you don't want to bother with this, and you just want to graph it from here. All right, well, you notice that the x squared has this axis of symmetry. You could fold it over that line there, right? So the axis of symmetry is given by negative b over 2a. So here's b. In this case, a is 1. So this would be a negative 2 over 2 times 1. This is negative 1. So what that says is our vertex, this thing, lies on x equals minus 1. So here is the vertical line, x equals minus 1. That's the axis of symmetry, okay? So what we know is that the vertex lies somewhere on here. It could be here, it could be here, it could be here. We don't know yet, okay? But we can find out. We have an x value. If you want to find a y value, you just plug it in there. So f of minus 1 would be minus 1 squared plus 2 times minus 1 plus 1. Minus 1 squared is 1, minus 2 plus 1, so this is 0. So our vertex, we said it lied on the line where x is minus 1. It's on here somewhere. And we just plugged in that x value to figure out the actual y value. It's 0, 1, 0. There's our vertex. Since A is positive, we know this thing opens upwards. There we go. Okay? So that's roughly what it looks like. Well, the next step to figure out what it really looks like, because does it look like this or does it look like this? The most convenient thing to look at is where it crosses the y-axis when x is 0. See, this line is where x is 0. If I made x 0, I get 1, right? If I replace x with 0, my f of 0 is 1. So that tells me, boom, right, 0, 1. So that way I know it looks like this. Well, again, that was exactly, what did I say? X squared, but shifted to the left by 1, isn't it? So this is the other way of doing it, right? If you don't want to bother completing the square, first step, find your axis of symmetry. All right, that's where you know the vertex lies. Plug that x value into your function to find the y value, and then you know where the vertex is. And then you want to find out where it crosses the y-axis. So you let x be 0, and then it's always going to be your c value. And then you know exactly what it looks like. All right. Now this one, what if I had something that was like, say, this? All right. So if I went through these steps, I'd find, oh, here's my axis of symmetry, and that's an x value, x equals something. I'd plug that number in, find out the y value, right? And then I'd let x be 0, and so I get the c value, and that would tell me that point. There's two other key points here. What are these points? We use the quadratic formula. That's where f of x is 0. The quadratic formula tells you where this thing is 0. So you use the quadratic formula and it'll give you the other key points. Okay. So notice some other things here. All right. Again, if A is negative, it's going to turn it upside down. So if my vertex is up here and A is positive, I don't have any x-intercepts. It never crosses the x-axis. If my vertex was down here and it opened upward, I would have 2 x-intercepts, right? Or it might just touch and just have 1 x-intercept, okay? And remember, the quadratic formula tells you about the x-intercept. So let's do another quick example. What if I have f of x equals 2x squared minus, let's do a negative. I'm going to flip this thing over. Let's do a negative 2x squared plus 2x plus 1. All right, let's say I don't want to bother completing the square. What does this thing look like? Okay, well, my axis of symmetry is at negative b over 2a. Remember, negative b over 2a, that's your vertex formula. Where the hell does it come from? Remember your quadratic formula. If this is 0, that's the same thing as saying negative b plus or minus the square root of b squared minus 4ac all over 2a. That's where your vertex lies, okay? So here we have negative 2 over 2 times negative 2. So this is 2 over 4, which is a half. So I'll call this 1. So here's a half. I know my vertex lies on that line. That's my axis of symmetry. Where does it lie on that line? Well, I need the y value. I have the x value. To get the y value, I plug it in the function. The function tells me the y value. So this is negative 2 times a half squared plus 2 times a half plus 1. So this is 1/4 times 2 would be a negative half. 2 over 2 is 1. So I have 2 minus a half, right? That's 1.5, or let's say 1.5. So my y value, my vertex, I knew the x value was at a half. That's why there's my axis of symmetry there. And I found out my y value is 1.5. So over here at a half, I go up. Let's see, if this is 1, and this would be 1.5. So boom, there's my vertex. All right. This is negative. So that means this thing opens downward. Does it look like that, or does it look like this? I don't know yet. The fastest way to find out is to figure out where it crosses your y-axis, okay? So where it crosses, right here, that's where x is 0. So if I let x be 0, I just get 1, right? My y-intercept is at 0, 1, because if I let x be 0, I just get 1. So 0, 1. So I know this dude looks like this. Boom. Well, there's two other interesting points here. What is this point and what is this point, right? Well, that's where the function is 0, right? That's where my y value is 0. So if I find out, set it equal to 0, solve for x, what are these x values? Well, we know the answer because we have the quadratic formula right here. It's going to tell us. So our x-intercepts are given by x equals negative b plus or minus the square root b squared minus 4ac all over 2a. So first off, I have negative 2 over negative 4, which is going to be a half. Now plus or minus 2 squared is 4, negative negative is a positive 8 over negative 4. I have 1/2 plus or minus square root of 12 over negative 4. So you all know how to reduce these. The square root of 12 is 2 times 6, which is 2 times 3. This is 2 squared times 3. This is the square root of 2 squared times the square root of 3. This is 2 root 3. Y'all done this before? Y'all should have done this stuff before. Because it's inside the square root, it takes 2 of them to come out as 1. Because it's square rooting. All right, so this is 1/2 plus or minus 2 times the square root of 3 over 4, negative 4, right? So I can continue to simplify this. This is 1/2. So think about this though. A positive times a negative is a negative, and a negative times a negative is a positive, right? So those, I can flip that. But you know what? Saying a plus or minus b, that's the same thing as saying a minus or plus b. These are two different numbers, right? Does this make sense? This is a plus b and a minus b. Well, this is a plus b and a minus b, isn't it? So that means when you have something like that, you could just throw that minus sign on the bottom away. Saying minus plus is the same thing as saying plus minus. All right. So let's simplify this. 4 over 2, this is root 3 and 2. So here's my two numbers, 1/2 plus root 3 over 2 and 1/2 minus root 3 over 2. So guess we're at this 1/2, that's your axis of symmetry. We already knew that was going to be right there. So this point here is, the x value is 1/2 plus root 3 over 2. This one is 1/2 minus root 3 over 2. That's the x value. The y value is obviously 0. We haven't gone up or down. That point is, right? Right here is 1/2. See, this thing here is telling you, okay, this is a length of root 3 over 2. This is a length of root 3 over 2. That's why the quadratic formula looks the way it does. There's your vertex formula that tells you your axis of symmetry. And then this part is just telling you the distance from the axis of symmetry to your roots. Okay, so that's how you graph quadratic. Let's look at another example here. What if I have f of x equals 2x minus 3x plus 4, right? I could complete the square and then treat it as a transformation, right? Or I could just do it the way we just did it. So the way we just did it, we find our axis of symmetry, negative b over 2a. So b here is negative 3, a is 2, right? There's your a, b, and your c. Yes, thank you. So negative 3 is just 3 and then 4. So let's treat each one of these as, I don't know, 3/4. 1, 2, 3. Make this 1, so this is 3/4. There's my axis of symmetry, x equals 3/4. All right, that's where the vertex lies, on that line. Where is it at on that line? Well, I need to plug 3/4 into my function. So I got 2 times 3/4 squared minus 3 times 3/4 plus 4. 3 squared is 9 times 4 is 18. 3 times 3 is 9/4. Let's get a common denominator. 9 times 4 is 36. 4 times, what was 4 times 16? 64. So, what is this? 64 minus 18. What is that? 64 minus 18. 64 minus 18. 46. All right, so way the hell up here at, yeah, I'll do it a little lower. Let's say up here, this is 46. Boom. That's where it's at. So let's, so my y here is scaled a lot differently. From here to here, I said it's the length of 46. So I could draw my vertex here. All right, so my vertex is at 3/4. Oh, no. I need 46 over 16. I forgot my denominator. So 46 divided by 16 is 2.875. My vertex is at 3/4, 2.875. So that makes things a lot easier. Let's say this is 1, 2. If this is 3, 2.875 is right around here. So boom, that's where my vertex is. The A is positive, so this thing opens upwards. But I need to know what this point here is. All right, what is that point? Well, if I let x be 0, this is where x is 0. If I let x be 0, I get 4. So 4. Now I got that. There are no x-intercepts. Isn't that weird? Not really. It opens upwards and the vertex is up there. Well, what about the quadratic formula? Didn't I say, well, if I set this thing equal to 0 and try to solve, well, it's never 0. Is it? Right? It's never 0. So what would happen if I use the quadratic formula? Look at the ugly part, that negative, the square root of b squared minus 4ac. That part, that's called the discriminant. For this example, look at what it would be. B squared, negative 3 squared minus 4AC. This is the square root of 9. 4 times 4 is 16 times 30 times 2 is 32. What is this? This is the square root of negative 23. You can't take the square root of a negative number, right? You can, but it's an imaginary number. So that's why it's called the discriminant, this guy. If the stuff inside is negative, you don't get any real roots, right? If the stuff inside is positive, then that's a number, and your roots are going to be the minus b. You're going to get this root and the other root, okay? The plus and the minus. Now, if this thing is 0, that's when you only have one root. If that's 0, that's when it's touching, all right? If this stuff is negative, then it's above the x-axis. It never crosses it. There are no real roots. If this thing is positive, you have two roots. This plus this, and this minus this. And that's how you graph quadratics. This makes sense. A lot of information all at once, right? But we could do a couple more examples here. All right. What happened to my other stuff? Yeah, we'll come back to rational functions. Let's do another example. Let's say f of x is negative x squared plus 2x minus 1. All right, the best thing you can do when you see these is write down your a and your b and your c so you don't screw it up, right? Your a here is minus 1, the b is 2, and the c is minus 1, okay? So my axis of symmetry is that x equals negative b over 2a. This is negative 2 over 2 times a negative 1. So this is 2 over 2 is just 1. So over here, at x equals 1, my vertex lies on that line somewhere. What's the y value? Well, let's find out. I'll plug the x value in. Let's see, I got a minus 1 plus 2 minus 1. That's 0, right? So boom, there's my vertex. My vertex is at 1, 0. The a is negative. So that means this thing opens downwards. Where does it cross? Let's find out what that point is. Well, that's when x is 0. Well, if x is 0, I get minus 1. So that point right there is at 0 minus 1. And luckily, this one, the vertex is the same thing as the x-intercept. There's only one. Well, what if I use the quadratic formula anyways, just to see? Let's see what it would say. Here's where my x-intercepts are. Negative b plus or minus the square root of b squared minus 4ac all over 2a. Negative 2 over negative 2 is just 1. 2 squared is 4. Minus 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 is a minus 4. And this is over a negative 2. Well, this is 0. I'm doing 1 plus or minus 0. So this is either 1 or 1. Well, what is that point right there? We already said it's 1, 0. All right. So that's why this thing is called the discriminant. It can be negative, it can be positive, or it could be 0, and it discriminates. It tells you whether you have no intercepts, 1 intercept, or 2 intercepts. That's why it's called the discriminant. Can y'all handle that? That's everything you need to know. You just need to do some examples. Practice a few of these. So you need to label the vertex, the axis of symmetry, the y-intercept, and the x-intercepts. You need to know, does it open up or down? If this is negative, it opens down. If it opens up, positive, if it's positive, it opens up. You can always do completing the square and then look at the transformations, remember? Like we did last time, you can always do that. Y'all good? Are we good on quadratics now? All right, let's move past quadratics. Go into the next section to rational functions. Let's see, let's cut. This page. Insert new page. Like this one. Select page. Cut page. Doo-doo-doo-doo-doo-doo. Paste it there. And so it will be that out the way. There we go. Graphing, section 2.4, rational functions. So examples of rational functions are like this. X squared plus 2x plus 1 over x plus 3. Or x minus 1 over x squared plus 7x minus 4. It's a polynomial over a polynomial. Okay? So we know how to graph at least quadratics. We haven't learned how to graph like, I mean, we know what x cubed looks like, right? They didn't ever tell us what x to the fourth or anything else looks like. Basically, the higher the power of x, the more wiggles. Okay. So if you have something like x to the fourth, you'd have 1, 2, 3, 4 roots, unless this thing's moved down below the x-axis. And x to the fifth would look like that. And if you had x to the sixth, you'd add another one. The more powers of x, the more roots. All right, the more wiggles. That's how polynomials are. All right. So how would we graph these? Well, the important thing to know is you can't divide by 0, right? Can't divide by 0. Okay. So what happens? Let's say I have f of x equals 1 over x. This is the simplest example of a rational function, right? The simplest function was f of x equals x, right? So the simplest rational function is this guy. What does it look like? Well, you can't divide by 0, so this thing is not defined at 0. So what I do is right here at 0, I put a dotted line because the function cannot cross that line. If I plug 0 in, it chokes. Does that make sense? If I put a dotted line there and I say, well, my function can't cross that. That's close. That's called a vertical asymptote, right? So let's look at what this thing does when I get close to 0. If I plugged in, say, 1, right? So over here at 1, at 1, 1 over 1 is 1, right? So that's a point on my graph. What about negative 1? 1 over negative 1 is negative 1, so that's a point on my graph, right? Just plugging in some numbers. Okay, what does this thing do if I plug in something really, really big? What's 1 divided by a million? Yeah, it's tiny, right? Right? If I plugged in 2, I'd get a half, right? 1 over 2. If I plug in 3, I get 1 over 3. If I plug in 4, I get 1 over 4. If I plug in a million, I get 1 over a million. So what this thing is doing is it gets closer and closer and closer to the x-axis. It never touches it, right? 1 over infinity is 0, right? But we never get to infinity. Kind of, yeah. But it's just a limit, right? As this gets bigger, this thing gets smaller. So that's why when we go to the right, it just gets smaller and smaller. So what about in this region? If I plug in values of x closer to 0, what does it do? If I plug in a half, 1 divided by half would be 2, right? Yeah, 1 divided by a third would be 3. 1 divided by a fourth would be 4. 1 divided by 1/1,000,000th would be a million. So this thing goes up. It just shoots off to infinity. It never can touch this dotted line because if I plug in 0, it chokes. So instead it just veers off. Let's look on this side now. Let's look way over here. If I put in -2, I get a negative half. So over here at 2, I'm at a negative half. If I plug in a negative 3, I get a negative third. If I plug in a negative 4, I get a negative fourth. If I plug in a negative million, I get 1 over negative million. So it's negative, but it's getting smaller and smaller. So this thing goes to 0, right, as this goes to negative infinity, but I'll say it goes to 0 from the left because it's a negative number. It's a very, very tiny negative number. We're talking about our y value here. Our y value is negative, but it's getting really small. So now let's look in this area. If I plugged in a negative half, 1 divided by a negative half would be at negative 2. 1 divided by a negative 1/3 would be a negative 3. 1 divided by a negative 1/1,000,000th would be a negative million. So it just veers off. So again, it can't cross the dotted line. So instead, it just veers off. All right, this is why you can't divide by 0. What is 1 divided by 0? Well, it depends on how you got there. If you're approaching 0 from the right, it's a positive infinity. But if you go to 0 from the left, it's negative infinity. So 1 over 0 is both positive and negative infinity at the same time. And there's nothing further apart than positive and negative infinity, right? Bad enough that infinity isn't even a number, it's a direction, right? But even if you were like, I'm open to directions, right? Doesn't have to be a number. Well, you're still getting 2 directions that are in opposite direction. That's why you cannot divide by 0. So that's what the graph of 1 over x looks like, okay? Does that make sense? You need to think this through and make sure you understand why it looks like that. By the way, this is what you would call a horizontal asymptote. The graph never crosses that line either. Okay? I don't know if they'll get into teaching you that. So what if I have something like this? F of x equals 1 over x minus 2. Well, this is exactly 1 over x, but shifted to the right by 2. Right? Remember your transformations? Yeah. And think about it. I can't plug 2 in, right? So if I was going to graph this, 1, 2, I can't plug 2 in, so that's where my vertical asymptote is. Otherwise, it looks exactly the same. My vertical asymptote is shifted to the right by 2. All the rest of the graph is shifted to the right by 2. So is the isotope always going to be minus? Not necessarily. Sometimes you have more. All right. But in this example, it's always like that kind of thing, like x minus or plus one number. Whatever you're subtracting from your x, if the x only shows up once, and you know you can relate it to this, so like x, if you had an x minus 4, that would be a shift to the right by 4, and so on. Yeah, yeah, that's part of your transformations. If you know what f of x looks like, then you know what f of x minus a number looks like. So that's what this is. This is exactly this function where I replaced x with x minus 2. Okay. So what if I have something like this? F of x equals x plus 2 over x minus 1 times x plus 3. All right. Whatever this thing looks like, I don't know exactly what it looks like, but I do know that I can't plug in a 1. And I can't plug in a negative 3. 1, 2, 3. So I know this thing has vertical asymptotes there and there. The graph can't cross those. So whatever the graph does, I don't know if it's down here or up there, but if it comes close to this, it either shoots up or it shoots down. Then in here, it's going to either be like that or like this, or it might do like that and then like that. Whatever it does, I don't know what it looks like, but whatever it does, it's not going to cross those lines. When it gets close to those dotted lines, it veers off because it can't, because that's where you divide by 0. That makes sense? All right, so I guess we should follow the book, right? Make sure I don't skip anything, like how to graph. All right, here we go. Let's back up a little bit here. So again, this is what a polynomial looks like. They use the letter A, I use the letter C because those numbers are called the coefficients, and the word coefficient starts with the letter C. So you might see the A, B. You could use any letter you want. All that is that's the number that you're multiplying your x by. The degree of the polynomial is the highest power of x. So our quadratics are second degree because they have x squared. Okay? The domain of a polynomial function. Those are the numbers you can plug in where something can come out. Well, polynomial functions like this one, x to the fifth or whatever, I can take any number I want, any number, and I can multiply it by itself 5 times. I can cube it, I can multiply it by 4, and I can add all those together, and I'm going to get a number. So the point is the domains of polynomials is all real numbers. If you graph it, they go forever right and left. All right, meaning you can plug in any number you want, and you're going to get a y value. So domain is left and right. The domain of a polynomial is all real numbers. Okay. So here's x minus 2. Here's an x cubed minus 2x. Notice there's crosses 3 times. Basically has 3 wiggles in it because it's an x cubed. This one's an x to the fifth. 1, 2, 3, 4, 5. It's got 5 wiggles in it. Okay. So that's what polynomials look like. They're just wiggles, curvy little wiggles. Here's some more. Can I read that? Kinda. Really? All right, this one's a quadratic, so obviously it looks like that, right? This one has x to the fourth. Well, it's got 1, 2, 3, 4 wiggles. This one's an x to the sixth, right? I can't just draw a line here to hit it 6 times, but you can see I got 1, 2, 3, 4, 5. No, it's got too many wiggles here. 1, 2, 3, 4, 5, 6, 7. I'm counting one of them twice. Anyhow, it should have 6 wiggles. Okay. We kind of get an extra one in there because it's been basically if you set this thing equal to 0 and solve for x, you would get 6 answers. Doesn't necessarily mean you have 6 roots because like up here, this wiggle is above the x-axis. Okay. So the leading coefficient, well, for this one, the leading coefficient is 2. For this one, since it's just x to the sixth, there's really a 1 in front of that, right? We don't write it. When you have x to the sixth, it's really 1 times x to the sixth, right? You don't bother writing 1. Well, since that's the coefficient for the highest power, that would be called the leading coefficient, all right? Polynomial is continuous, so polynomials don't have breaks. Like a rational function, we saw it broke. There's like a big red dotted line. That would be a non-continuous function. All right, continuous functions are the ones where you can draw it without taking your pen off the paper. All right, that's a continuous function. Those are our favorite ones. So there's your vocabulary. Okay, discontinuous. This thing is discontinuous. It breaks from there to there. It's a discontinuous function, right? This is continuous, but it's not what we would call smooth. See that jagged edge? So this is a continuous function, but it's not smooth. So our favorite functions are continuous functions, right? That are smooth, continuous and smooth. This one doesn't satisfy smoothness. They don't say anything about being smooth, but they just do want to point out some functions have sharp corners, and that causes a problem. Y'all know about slope, right? Well, at this point, there's no such thing as slope. We know the slope of this, we know the slope of that, but right at that point, there's no such thing as slope. It could be anything. And we don't like functions that are not differentiable because the derivative tells us the slope of a function. Right there, the derivative doesn't exist. You'll learn about this in your next class, so it's important to know. Start points suck. Oh, the weight of a fish. We'll do that next time. For your exam. Daily exam number 10. So since you know how to graph quadratics, graph 2x squared plus 3x plus 4 to g of x equals negative x squared minus 2x plus 1. Now, when I say graph, I mean, I want to know what the axis of symmetry is. I want to know what the vertex is. I want to know what the y-intercept is. And I want to know what the x-intercepts are. All right? Huh? Yeah. Label axis of symmetry. I think I need another N in there. All right. Label that. The vertex, y-intercept, and x-intercept. Okay. And show your work. I mean, you could plug this into a graphing program, right? And then just draw it and then try to trace it. You know what I mean? Don't do that. Show the map. Actually find out what the vertex is. All right. Remember, axis of symmetry is your negative b over 2a. All right. So just follow the steps that we did. You can look in any book, including the one that you have, and it'll list out the steps. All right. There's only two of them. You can do this. Remember, this one's going to open downward because A is negative. Okay. Yeah, if A is negative, it opens downward. If A is positive, it opens upward. Just like remember x squared opens upward. That's because A is 1, positive. You know, I mean, you can do the completing the square method and do transformations, right? Yeah. Because once you do the transformations, it's still hard to figure out where is the vertex. Yeah. I guess it's just as easy. Because the vertex is the h and the k. Because whenever you do this, whatever ax squared minus h plus k, you turn it into that. There's your vertex. That's your x, and there's your y. All right. You could find out your y-intercept, because if you replace x with 0, it's this times that plus that. Up here, it's easier. If you replace x with 0, you just get 4. Down here, if you replace x with 0, you have to do arithmetic. Yeah, so trying to figure out your y. I mean, they're both convenient in their own right, but they highlight different things. I think with this method, you have to use the quadratic formula, or you can factor. Do that too. The other thing is, instead of completing the square, you also, the other way to factor is to turn it into something like this: x plus a number and x plus some other number. Right? When you set that equal to 0, you know the solutions are negative that and negative that, which we'll be doing in another section, I'm sure. Lots of factoring. Y'all are good to go whenever y'all want.